All right, so we're going to start with what is the introduction chapter in the textbook. Am I unmuted? Yes, I am. I really love this introduction chapter. I think it's really approachable. Okay, so who here has ridden on either BART or Muni in the city? Yeah, great. So you've seen a map like this, but we've got two maps here. So what I want to know is what's the difference between these two? What do you think? What can you say about both of these maps? Yeah. 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 So like the one on the right is definitely more real life. Here's all the streets and here's like the geography. We've got like parks and stuff. Anything else that we can say about the difference between these two?
The one on the left is much easier to understand.
Yeah. So yeah, because this tells us more of what? Like here's the stops that you need to keep in mind. I wanted to get a picture. There's one if you go like on the train, there's like a really like a horizontal one. If any of you go to the city and if you want to take a picture of that and send it to me, I would really appreciate it. But it's like a much more simplified version of this, right? So this is fairly complex compared to what's actually in the train. So you can simplify it further. Anything else that you can think of? Yeah. So the thing on the left is we're looking at what are the lines, what are the stops, where can you transfer? Those are like some of the three most important things about the map on the left. And the map on the right also, if you zoom in, I think it also kind of has that. But it's much simpler to read with the map on the left. And there's something also like that with BART, where this is like the simplest map that I found, but also if you go into the BART station, it has like a simpler version that it shows in like the condensed space. But it's the same idea where we've taken this information and only extracted the relevant details. What are the stops? What lines are there? How do you get where you're trying to go, just in terms of the BART stations? And that's the main idea with what we're going to do with graphs, where we are going to work only with the important information. So this one is a graph of cities. So each dot that we've got, that we've labeled it as a city. So we've got San Francisco, we've got LA, we've got Phoenix, El Paso, Memphis, St. Louis, and so on. So each of these dots is a city, and then there's a line between them. Probably like this is something that you can directly access by like a highway or something. So like we can drive on I-5 from SF down to LA. But maybe if we want to go to Salt Lake City, we have to go through Reno. So something like that. So a graph is a way of only representing the important information. So there's the first problem in your packet. And so I would like you to get together with your neighbors and answer just that first question. I'll come around and collect the extras. The other thing I'll mention with these is that I'm not expecting that like you get the answer correctly. This is mostly just our fun, explore, see what we can do. All right, how are we doing? Anyone find any guesses for LA to Amarillo? 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 Yeah,
I got 25.
25. Wait, so what cities?
So I went from LA to Phoenix, and then from Phoenix to Albuquerque, and then from Albuquerque to Ontario.
Mm-hmm. And that's shorter than just going directly to Albuquerque, right?
Yeah.
Yeah. Anyone else? Cool. Any ideas for Omaha to New Orleans? Yeah, go for it.
28.
28. What cities?
One's on the outside from Omaha, Kansas City, St. Louis, Memphis, and then New Orleans.
Mm-hmm. Anybody else have any ideas? Not that's cool. Um, any ideas for SF to Denver? Is it faster to go to Albuquerque and Denver? Like more direct route? No? What do you think?
I
Oh,
went
I'm sorry.
San Francisco, Reno, Salt Lake City.
Yeah,
and
like go up and around.
Yeah.
Yeah. Cool. Yeah, so this is a graph in which we've embedded like maybe driving time as the numbers for these connections. So we've got nodes, which are the vertices, and those are the dots, and then we've got edges between them, and we've said that associated with an edge is maybe the driving time. Okay, so we could also apply graphs to something like chemistry, where with chemistry, the if we have a molecule, we can draw like the diagram on paper, like the ones on the bottom here. Um, but there's some abstraction that's happening here, where this diagram on the bottom doesn't tell us how it's arranged in space. So the actual like image of the molecule doesn't really correspond. Like we've removed some information when we're writing the diagram. That's something to keep in mind. We've extracted only the relevant information for us. Okay, now it's time for that math problem guy. So you may remember in high school or something where you have someone who buys 50 bananas or 500 watermelons, something like that. So I'm going to try as much as I can to give these math problem guys names. So we've got, for example, Gertie Graffer, we've got Floyd Pathman, and Euler Edge Traverso. Floyd and Euler, those are famous graph theory guys. But yeah. So we've got a really famous problem called the utilities problem, where let's say we've got Gertie, Floyd, and Edge, and these are all three neighbors who hate each other. And they want to, there's three utilities. There's gas, water, and electric. And they want to connect each of their houses to all of the utilities. But because they hate each other, they don't want any of the utility lines to cross. They're like, that's my domain. I want all of these lines to myself. So the next packet problem is, can you draw? So we've gotten it started for you where Gertie's house is connected to all three. Edge's house is connected to all three as well. But Floyd is only connected to gas and electric. So the next question is, can we connect Floyd's house to water? Talk about it. Without the edges crossing. All right, what do we think? What are your ideas? Can it be done? You shrug. Yeah, this is a really famous problem. Most people would say no, asterisk. Where when we're drawing it just on a like a flat sheet of paper, it is impossible to draw to like connect Floyd to water without any of these lines crossing. That's when we're drawing it on a flat sheet of paper. Does that maybe give you any ideas for how we could make this possible? Right. So it's impossible only if we're on a flat sheet of paper. there's some, if you look up like 3 utilities problems, there's some, there's a solution where if you have like what's called a torus, basically a donut, if you embed things on the donut, if you like have, here's house A, B, C, here's utility A, B, C, then you can connect it on a donut without things crossing. So that's something to think about. Like maybe it's not possible, the solution as we've formulated it with our restrictions, but it may be possible another way. So I'll always kind of be thinking of what are the assumptions that we have right now? And if it's not possible this way, how could we approach it from a different direction? Okay, so the next problem, so let's say we're working with a circuit. This isn't a real circuit, it's just a drawing. But in a circuit, we typically have connectors that have to be flat and can't cross each other because then that causes problems. And so this is where something like the 3 utilities problem is really important, where we need to be able to say which is, how can we make this not cross each other? That's something called planar graphs, which we'll look at. So we've got problem 3 in the packet. This should be fairly quick. So go for it. And the idea here is that with graphs, you can move things around. So in the packet, there's like A, B, X, Y, Z with the dots, and you can move the dots around. And when you move the dots around, that changes, like the edges don't change, the connections don't change, but the orientation of them can move. Okay. So let's look at this one. How can we, what do you think? How can we redraw for which one, first of all, what's the answer? A or B, can we redraw? Yeah. A. Yeah, that's correct. Why is that? Okay. Diamond with a line through the middle. Let's, yeah, let's see. So actually here, let me have you. Yeah, it's hard to like talk it through. Go for it. Yeah. Yeah. Okay, let me see if I can replicate that. So we've got A, B, and then X, Y, Z. Okay, so let's double check. So A and B are not directly connected, nor are they here. X, Y, Z don't have any edge between them. Yeah, so it's like we just took B and like we take B and move it like over here. Yeah. The other way I was thinking of it is you could take Y and like drag it over here. Like if this is Y, then we have A and B. No? Ah, no. Sorry. Wait. Thank you for telling me. There we go. Yeah, so over here, this is what you drew. The other option is to like take Y and like move it off to the left. Anybody else had a different idea? Sure. Oh, wait, yeah, because you still need to move B. Yeah. Yeah, so if we have like Y over here, then A, B, then we've still got X and Z. So A goes to X and to Z, B goes to X and to Z. Yeah, so you do need to move one of those again. Yeah, there's lots of different configurations to this because like we've got these options and you can just like move it over here, draw it a different way. So if I do ask you to draw like a graph on your homework, the configuration of the graph doesn't really matter, like the way that you've laid it out. The really important things are like, are all the edges that are here also in here? Like, do the edges and vertices match? Okay. Let's try this. And okay. So the other thing we need to talk about is abstraction. We've got maybe 10, 12 minutes left, so we're doing good on time. So abstraction is a word you may have heard before, but it's going to be really important to us in this class. Where abstraction is, some possible definitions that I got from Google are the process of considering something independently of its associations, attributes, or concrete accompaniments. Another is freedom from representational qualities. That's more like in art, but I also kind of like that one too. The quality of dealing with ideas rather than events. So the common ideas in these definitions are abstraction is the process of kind of rising above, where down below we're looking at the details. So I've got this thing here of if we're looking at a heart and we're trying to abstract this drawing of a heart, maybe one of them is this is like an anatomical art where the next level of abstraction is just like the cartoon emoji heart. And then the next level is where we just have a square. And then the arrow also gets abstracted to something more cartoony, to just like a line. Right? So abstraction is kind of rising above details. That's what I want you to be able to do in this class of looking at a situation and asking, what's the really important details here? Because we don't need all of them. One of my analogies is I took these pictures in Yosemite. The left one is from like the valley floor where I'm standing on the ground and I take a picture of Half Dome. And you can see like here's a traffic cone, here's the road. You can see like the trees. This is a tree, this is another tree. There's like yellow caution tape to stop you from going off the path, stuff like that. But when you go up to, I think it was Glacier Point, and you look down from the top, like from the top of the valley, those things fall away. You don't see traffic cones. You can kind of see cars, and like maybe little specks of people, but it's like that's abstraction where we've risen above and we're looking at, oh, here's the mountain, here's the valley. There are trees in the valley instead of this is a tree, that is a tree, that is another tree. That's abstraction. We're taking the mountaintop view. We're rising above and looking at what are the general and important qualities that we actually want to do to work with. And that's what the BART math is. We've risen above. Here are the streets that you want to take. What are the bridges that you're going to cross, to just here is the station. We go through like under the water and we show up in San Francisco. That's the idea. Okay, so it's time for words. So the first important word is a vertex or a node. You'll hear me use those pretty much interchangeably. I tend to prefer vertex, but vertex node either works. If you're looking for like at graph theory textbooks, typically you'll see vertex more often. If you're talking more to computer scientists, tends to be you'll hear node more often, but they mean the same thing. And so a node is a drawn dot or a point. So like each city in the first problem, that's a vertex, a node. A small note, the plural of vertex is vertices. The singular of vertices is vertex. So it's not vertice just by itself. The singular of vertices is vertex. Nodes, that conjugation is easier. Yeah, so typically we'll represent it by like a dot, like connect the dots, or a small circle and you don't fill it in. That's mostly up to personal preference. An edge or an arc or a line, it connects exactly two dots. You'll mostly hear me say edge, sometimes line, but once we're talking in graph terminology, I'll say edge because that's the like the more rigorous term for that. I don't know that I've really seen anyone use arc. You can if you want to, but vertex and edge are the main ones that we're talking about. But again, any of these three are interchangeable. So I think I have, oh wait, sorry, I missed one. Sorry, I missed one of the problems. All right, let me go through the rest of these definitions and then we'll get to the two problems. So an edge connects exactly two vertices. A graph is going to be defined by two sets. It's going to be defined by the set of vertices and the set of edges. We write that graph as G equals V comma E. I know this is a lot of terminology. We'll use it a whole bunch, so we'll go over it again and again. And we say two vertices, so two dots, are adjacent if they're connected by a line. So like in the first problem, San Francisco and Los Angeles are adjacent, right? We can go, they're connected directly by a line. But let's see, San Francisco and Vegas are not directly connected by a line. We have to go through a path of cities otherwise to get there. Okay, so we've got 5 minutes left. So let's maybe finish out with problem 4 in the packet, and then we'll start with problem 5 next time. So talk with your neighbor, work on problem 4. And then maybe we'll come back and share if we've got time before the end. Right, I'll maybe have us stop there. Because I want us to share different ideas. So next class, bring this, don't lose it. Bring this and we'll get back in groups and share. I want to mention one thing before we go. I do have an assignment that's due on Thursday. This is your lab 0. I have this for every class, which is basically who are you, what classes you've taken, anything you need me to know about you. Maybe like the office hour schedules don't work for me. I'm going to be booking a lot of appointments with you, or something like that. So fill this out. It should take 5 minutes, and get that into me, and I would appreciate that. All right. Thank you for coming. I will see you on Thursday.